All right, so this is just a quick video to review some of the big ideas that have come up during this unit. We're talking about forces, and so I have just a quick sketch here of a man inexplicably pulling a car, and the purple line represents the ground that they're standing on, and then that horrible colored monstrosity is supposed to be the planet Earth itself. It has a yellow core and, the mantle, and there's like some brown and some anyways. So that's what's going on in that picture. So I'm going to use this picture to help us start talking about what we know about forces. One of the big ideas that I'm hoping you've grabbed this school year or this unit so far is the idea of drawing free body diagrams. So I'm going to draw free body diagrams for several of the objects here. The first one I'm going to draw is the free body diagram representing the car, or the person, I'm sorry. So the person has a couple different forces acting on them. One of the first forces that they have acting on them is the force of gravity. So the force of gravity is pulling that person down towards the center of the Earth. I'm going to do yellow for the Earth, because, I don't know, the core is yellow, whatever. Then it also, because this person is standing on the surface on this purple sidewalk, whatever, there is a force that is pushing them upwards, that contact force between them and the ground. And we call that one the normal force. As they're pulling on that rope, they're pulling the car forward, but that means that the rope itself is dragging. Oops, that was weird. The rope itself is going to drag them backwards. So there's the force of tension from the rope. You can imagine that if you were pulling on a rope, you would feel the rope resisting your forward motion, which means since it's pulling back, it's, literally pulling back on this person. Finally, I probably should have made that blue. Maybe make that blue real fast, because blue is really it's the car that's doing it. So I'm trying to match the colors of these vectors to the objects responsible for them. And then finally, the last force that's acting on this person, and the one that lets them stay in place, is the force of friction that actually is pushing them forwards, resisting them moving backwards because of the tension. Again, that was weird. Okay, so we have a lot of stuff already done here. Let's start talking about this in terms of Newton's laws. Newton's first law, and I wrote it down the full text in another video, but Newton's first law states that an object in motion will stay in motion and an object at rest will stay at rest unless acted on by an outside force. So let's look at some of the objects we have in here. I think the easiest one to do this for is for that car. That car is going to stay at rest unless the forces acting on it are sufficient to force it to move. Otherwise, that car is just going to stay there forever, and the only thing that it will ever do is fall apart. And the falling apart is still following Newton's first law, because the parts are falling downwards because of the outside force of gravity. If we actually just left this in space far enough away from any planet that we can basically ignore the force of gravity, even if something happened to the material to cause them to no longer be attached, the door would still stay next to the car, because there's no outside force making it fall off. It would just all stay the way that it is. The same thing would be true if this car was slowly creeping forward, like it had gotten a push and we're pretending that there's no friction in the bearings or anything. So the car would just keep moving, and the only way for it to stop moving is the outside force of this person pulling on it. So the only way that an object ever moves is that it has an outside force, or an idea that I want to put in here is that we have some unbalanced forces acting on it. Unbalanced. Oh, darn it. I don't know why that's happening. Still happening though. Something wrong. All right, sorry if you've been watching me or hearing me make horrible sounds. But All right, I managed to write unbalanced force this time. So if there's some outside unbalanced force that's acting on the system, it will cause it to start to accelerate and move in some new way that it wasn't moving before. That applies to things that speed up, things that slow down, and things that change direction. Anytime that you see something speeding up, slowing down, or changing direction, there must be an outside force that is unbalanced by other forces that's causing it to move. Just to be clear, hopefully this is, I already said something that got you to understand this, but I'm kind of referring to the idea that in the case of the free body diagram that I've drawn so far, the force of gravity and normal force aren't going to create motion. They are outside forces, but because they're currently balanced, they're not going to really do anything. So that's Newton's first law, and I want to just remind you of, well, just to say, you want to be watching for changes of speed or changes of direction. That indicates those outside forces. If something's moving at a constant speed, it doesn't need an outside force. That's just an object maintaining the same motion behavior that it's had from some previous event, but it has no current forces that have to be acting on it. If something is speeding up, there has to be a force acting on it. If something's slowing down, there has to be a force acting on it. If something's turning, there has to be a force. But if it's at rest or if it's moving at a constant speed, it either has no outside forces or all the forces that are acting on it are currently balanced. So that leads us into Newton's second law, Newton's law number two. And Newton's law number two is the very simple, yeah, my computer's still acting up. That's a bummer. The simple idea that acceleration is the sum of the forces over the mass. So that tells us not just that it is accelerating, which is kind of what we used for Newton's law number one for, is this thing moving and why is it moving? Newton's law number two tells us how much. It says, okay, we've identified that there's this mass that exists. Now, how much is it going to speed up or how much is it going to slow down? So we do the sum of the forces over the mass. In this case, we have to do it in separate directions. So I would have to figure out the acceleration in the x direction and the acceleration in the y direction separately. So that's so annoying. Acceleration in the x and acceleration in the y. So that would be something like force of friction minus force of tension on this man all over. Oh my goodness. I'll just keep trying, computer. I'm more stubborn than you are. Over the mass of the man. And if we're doing in the y direction, it's only the ones that align with the y-axis. This is great. I hope you guys are enjoying this incredible video of watching me fight against the computer. Normal force minus the force of gravity. Oh my goodness. I don't know why it's doing this. It's kind of odd. Hold on. That was weird. Okay, so that's what's happening in the y direction. Sorry about that long pause and whatever. I'm sorry. Now that's what Newton's second law is used for, is finding how the object is accelerating and by how much. One other important rule is the direction of the net force. No, it's doing it again. The direction of the net force Ugh. I don't know what's going on with my computer. The direction of the net force and the direction of the acceleration are always the same. They always go in the exact same direction. So if you know that the net force is forwards, you know the acceleration is forward. If you know that the acceleration is, like at a right angle to the velocity because it's turning, then you know that the net force has to also add up. We'll do a little bit more with that next when we learn about circular motion and gravity, but now you're aware of that. The last rule, Newton's third law, and I'm really sorry, I meant to draw this, but I've already seen the way this is going, and I'm not going to try and draw it out. Instead, I'm just going to tell you guys the idea, and that the idea here is that all of these forces that I've drawn for this man have a matching equal and opposite force. So if I was drawing the free body diagram for that blue car, there's a force of tension pulling it forwards, and the force of tension of the man on the car is equal to the force of tension of the car on the man. They're just opposite in direction. So the car is being pulled towards my right, and the forwards for the man, I guess, and the man is being pulled backwards. There's also equal opposite forces for the normal force. The force of the ground pushing the man up is matched by the man pushing the ground downwards. The force of friction as the man pushes against the ground and is like with their feet pushing the ground backwards is matched by the force of friction of the earth, of the ground pushing him forward. That force of gravity pulling downwards on that man is equal to a force of gravity of the man pulling upwards on the earth. So there's always this equal and opposite pair. The common misconception and the place that is a stumbling block is not the fact that the forces are the same. Because if we're talking about, say, a big vehicle hitting a small person, the force is the same. And I need you guys to believe that and trust that and work on accepting that. The difference between them and the thing that you know would be different would be their acceleration. So this goes back to Newton's second law, which says the sum of the forces over the mass. Well, the force on the person and the force on the car would be the same, but because their masses are so different, their accelerations would be different. So when you see somebody, well, hopefully you don't see this, but if you see somebody get hit by a car and go flying, it's not because they experienced more force than the car did. They experienced the same force, but they have so much less mass that they go flying and the person stays still. So that pretty much covers everything that I wanted with this video. I apologize that the audio might have been weird and other stuff might have been weird, but I'm hoping that this is still helpful to you while you're preparing for your exam. So I'm going to pause it here and